Cool. Well, hi everyone. It's great to see so many people interested in containers. I guess that's not really a surprise in San Francisco, but it's great to be here. So today I'm going to talk about a few topics. I'm going to talk about Docker, data, and extensions. And I will cover Powerstrip, which was in the original talk title. So I think we can all agree that Docker is great. It is a fundamentally better way. It's a fundamentally better abstraction for applications. And in fact, containers in general are a fundamentally better abstraction for containers. Now, some things, however, are difficult to do with containers today. Multi-host applications, almost by definition, as soon as you want to run an application in production, you want to run it across multiple machines. And as soon as you move to multi-machine orchestration, you need to use some orchestration tools, and we've heard a lot about those today. But few of these tools handle state. Not many of these tools today handle the problem of data needing to move around with a container in a group of machines. So I'll talk a little bit about that problem and what we're doing to tackle it. So to sort of motivate this, modern applications, increasingly, there's a big trend to build applications as sets of microservices. So this is just an example of a microservice that I saw when we were doing customer development last year. And we saw that, like, even something... So this was really... this is a big simplification of the microservice that I actually saw. I was doing a Google Hangout with this guy, and he had this massive diagram with all of these different moving parts. And he said he was doing stateless 12-factor application development. But I was like, but you've got Mongo in there, and you've got MySQL in there, and you've got all these different pieces that aren't stateless. So at the moment, when people are building microservices, containers help them capture the stateless bits. And that's great. It captures the bits on the right-hand side of this diagram. I don't know if you can see the writing, but it captures this sort of API servers and web front ends if they're being built in a 12-factor way. But it doesn't capture the RabbitMQs or MongoDBs or MySQLs and Postgres's. And I think that there's no reason not to try and containerize all the things. We should be able to capture an application in a Docker Compose file or whatever your favorite flavor of YAML is to capture the entire app and then be able to reliably reproduce that entire application across multiple machines. Reliably reproduce that application on your laptop in a staging environment and then push it out into production. So that's the problem we're solving at Cluster HQ. We're solving the problem of managing stateful containers in production, solving the problem of being able to move containers around and still have them reference their data. And to motivate that problem a little bit, the problem with volumes in Docker, like today, and in general with containers, is that Docker best practices recommend that if you have a stateful application, that you store the state for that application in an external volume. That's the Docker run -v flag. And as soon as you attach a volume, and it recommends that you attach a volume from the host into the container. And as soon as you do that, you've stuck that container on that host because it now is... That host has become special. It's a host that has some data written on its file system that container cares about. And the whole, so Randy Bias came up with this great phrase, I think, that we should, in the cloud, we should treat our servers like cattle, not pets. So has anyone not heard of that phrase? Okay, a few people. So the idea is, like, in the cloud, you should assume that your instances are going to die. You should assume your infrastructure will fail because it does. It's fallible. Like, you're running on hardware at the end of the day, even though it's virtualized. And so when the hardware goes away, you want to be able to treat your set of machines that make up your application as if it was cattle. And with cattle, you number them. You don't name them. And if one of them gets sick, then you don't really get too sad about it. You just shoot it in the head and get another cow or whatever. So this metaphor applies to servers as well, and so you don't want to have servers that are pets, because when you have a pet, you name it, you care about it, and if it dies, then you get sad. And the same would be true of your production Postgres database. So it would be great if we could treat our servers like cattle, not pets. But with this problem, where if you mount a volume from outside a container into a container from the host onto that container, then that host has become special. It's become a sort of snowflake server. And we also care about ops. So Docker's fantastic in that it's grown up out of this sort of massive tide of developer interest for people wanting to containerize applications when they're developing them and have a consistent dev environment. But that has meant that until recently, there hasn't been so much focus on actually running Docker in production and having to care about managing services that are Dockerized from an operational perspective. And one of the key things that operations people know is that you need to be able to move things around. So I used to run a hosting company, and we had 3 machines in a data center in London, and it was a real pain to do maintenance on one of those machines because we didn't have virtualization. It wasn't possible to just say, oh, move this VM from one physical node to another. And so when we did maintenance, we had downtime. And then virtualization came along and it solved this problem, and you had vMotion for VMware, and ops people became happy. And now we've got containers and we don't have that anymore, so we're going to make the ops people sad. And therefore, we came up with Flocker. And what Flocker is a way of moving stateful containers around between machines. So you can deploy a set of containers onto a set of hosts, and then you can later move those stateful containers around between those hosts. And so Flocker comes in 2 bits. There's the Flocker client in this diagram on the left-hand side, where the user is typing something like Flocker deploy on their laptop. And that consumes 2 files. It consumes a fig file, or a Docker compose file, and a deployment manifest. And it puts those 2 together and logs into a set of machines on the right-hand side and looks at the current state of those machines, and if necessary, it moves some of those stateful containers around. And it does that with various different storage backends. One of them is our ZFS backend, and ZFS allows you to do snapshots and send and receive. And so we use that as the mechanism for moving those stateful containers around. So Flocker comes as an application manifest, a deployment manifest, the client and server components, which you install on your laptop, and then you go and install on some servers, either physical servers or in the cloud. And it sort of gives us this storage layer. So it gives us this storage abstraction. And so in this example, I'll show you how we can move a MongoDB container that's running on one machine to a different machine without interrupting, or only interrupting for a very short period of time, the Nginx container that's running, that's trying to talk to that MongoDB. And the way that works is that we do this thing that we call a 2-phase push, at least with our default backend, which is the ZFS backend, which is where we take a snapshot of the MongoDB container's volume while MongoDB is running. And then we replicate all the data using this ZFS send stream onto another machine. And when that ZFS send stream has completed, the MongoDB container is still running, it's still receiving writes, and it's still modifying that file system. So there will be some delta between the snapshot that made it over to the machine on the right-hand side and the current state. But then we quickly shut down the container on the left-hand side. We take another snapshot, and then we replicate just the delta between the first snapshot and the second snapshot over to the machine on the right-hand side. And then we start up the container. And we do all of that really quickly, and it's really helpful that containers are really fast, because it means that we can do that migration with only a few seconds of downtime. And so just quickly, I'll show you a demo of that. I'm not sure if that text is visible. I hope it is. But we've got 2 machines on the left. These are just VMs running on my laptop here. And we've got Docker running on both of those machines. And we've got a fig file here on the right-hand side that references a Docker image. It references a volume for a MongoDB container. And so that's pretty important. We've also got 2 of these deployment files. So deployment file 1 on the left-hand side has MongoDB under the first IP address, and deployment file 2 on the right-hand side has MongoDB on the second IP. And so we can see that Mongo is currently running on node 2. and we can log into Mongo using the Mongo client. And then because I can never remember the commands, I copy and paste them from our docs. But there's an example there. And you can go and see, well, hey, there's some data in our database. Great. We care about that data. Probably don't care about this specific data because it's just test data. But in general, you care about your data in your databases. And so I recorded this demo for Docker London. And so I'm inserting the data, hello Docker London again. And this is all while the Mongo instance is running on the machine on node 2. It's writing data to its volume all the time. And then what we can do is we can run Flocker deploy and move that container onto node 1. So what I just described about how Flocker works is happening right now. It's taking a snapshot of Mongo, replicating that snapshot to the other machine, shutting down the container, replicating the delta, and then starting up the container on the other side. And the other thing we do is we've got this very, very basic network proxy built in as a default network option that will just route all the requests to all the requests from Mongo to that machine, or the current machine. And so we can see that Mongo is now running on node 1. And this is really sort of the missing piece that we didn't have before, is that the data has moved with it. So we've got that second hello Docker London record in the database, and so that's demonstrated that we can move stateful containers around. So that's Flocker, that's what we're working on. We're also working on a bunch of other stuff. We have an API which we just landed in 0.4. So this is getting towards being production ready. There's an API that you can use. The idea is that multiple developers on a team will be able to consume the API in parallel and concurrently and spin up different applications on different machines, and that's all good. We're also working on pluggable backends, so we're working with a large set of different storage vendors to not only have our, what we call the peer-to-peer backend, which is the ZFS backend, which is kind of neat because it allows you to migrate stateful containers between cloud providers and stuff, but also a lot of people have an investment in an existing storage system, or they're running on cloud infrastructure, in which case they can take advantage of things like EBS or Google Compute block devices. So we're adding block device backends as well. And that's all great, except that there's a problem. As a company, we want to solve data problems. We want to really just focus on data. But what I just showed you was this sort of early version of Flocker where we had to manage a network layer. We had to manage, in a sense, orchestration, because we were saying, like, it was a very, very basic form of orchestration because it was just statically assigning containers to machines. But we don't want to solve orchestration. There's lots of other people working on really good orchestration systems. We don't want to solve scheduling. We don't want to solve networking. We just want to focus on data. And to summarize, it'll be good for us if more customers can run Docker in production using composable tools. And we don't want to have to land this monolith on people, say you have to use Flocker and nothing else. We really want people to be able to use Flocker with Docker Swarm, for example, or Fleet from CoreOS, or Kubernetes, or Mesosphere. And so that's the problem I'm going to address for the remainder of the talk, and talk about some of the progress we've been making, working closely with our friends at Docker on solving that. But first, a little bit of context. So let's talk about Docker in production. We already agreed, I hope, that real applications run on more than one computer. So if you've got an application that's deployed across multiple machines, then my view of the world is that there are 4 big problems that need to be solved to take Docker from a single host environment to being a multi-host environment. So the first problem that needs to be solved is composition. And the reason I put a picture of a fig up there should be obvious. There's a great tool called Fig that was acquired by Docker and turned into Docker Compose. And that allows you to express an application as a set of connected containers. So this is incredibly useful for people. Instead of having to type lots of Docker run commands, they can now have a file that they can put in version control, which allows them to describe their app in terms of the Docker images that it consists of. They can describe the complex sort of microservices architecture I showed earlier in the slides using just one file and referencing these Docker images. So it's really powerful. And Kubernetes has its own version of this sort of Fig format that they call the kubelet. And basically, there's lots of YAML and JSON flying around in this universe, but people are happily composing their multi-container applications. But until they can run their multi-container applications on multiple hosts, you also need another piece of the puzzle, and that's called scheduling. Scheduling is basically just deciding where to put containers when you run them, but across multiple machines. And I also think that schedulers have certain other responsibilities, such as trying to recover when actual machines fail, trying to reschedule containers to keep hosts balanced as well. So if one of the machines is really overloaded, it'd be great if either automatically or manually the system could move some of those containers onto less loaded hosts. So there's the whole sort of scheduling universe with Docker Swarm, Mesosphere, and Kubernetes all playing their part there. And it's great to have choice. And on networking, this is the third big problem that needs to be solved. There's the question of, well, okay, you've deployed these containers, and Luke Bond referred to this in his previous talk, and talked in detail about the two options. You need containers to be able to find each other, and they need to be able to talk to each other. And so there's console plays a part in service discovery. Weave is great if you want to give containers sort of first-class network identity with IP addresses. And of course, there's companies like Socketplane that are now working on the Docker networking effort. And then finally, the fourth problem that you need to solve to run Docker in production is storage. Because stateless containers are all very well, but data is at the heart of every real application. And the promise of Docker is portability. So if you can really move your application, including the stateful components, from a small environment on your laptop to a staging environment, and then deploy into production, potentially across multiple clouds, or at least being able, not being locked into certain cloud providers, then that'll be really helpful. So if you sort of squint and take a step back, it kind of feels like these four pieces are coming together. There are lots of different components in the ecosystem which should all be able to work together. And so I love this tweet from Adrian Collier, a good friend of mine back in the UK. He says, now the Docker ecosystem needs to work together to enable these solutions to be used, to be composed. For example, I want to be able to run Kubernetes with Flocker and Weave. And why not? You should be able to. And so this is the heart of the problem I mentioned earlier. So the sort of general picture for these systems that people are building, if you sort of abstract it a little bit, is that you've got some orchestration and scheduling system at the top, which will be fed by something which can do composition. So, for example, Docker Compose might talk to the scheduler up front. It's not on this diagram. And that orchestration or scheduling component will fan out requests onto multiple hosts. And the way it fans out those requests is by using the Docker Remote API, typically. And the Docker Remote API allows the orchestrator to say, oh, I'm going to run that container on that machine, or I'm going to run this container on this other machine. Or maybe I've detected that this machine has failed, so I'm going to reschedule the containers that were on that machine onto a different machine. And so we came along and we were like, okay, we want to work on some storage stuff. We want to make it possible to do portable volumes for Docker. And also the Weaveworks guys came along and they said, well, we want to extend the way that Docker can do networking. And so the problem here is that there isn't anywhere on this diagram to put these pieces. It's not currently possible to do interesting storage stuff or do interesting networking stuff without wrapping Docker. And so here's a lovely picture of a car in Bournemouth in England that got wrapped, just to demonstrate that wrapping sucks. It's not nice if you have to have multiple different command line interfaces competing for the end user in order to use these different tools. Because, as we said, we need all four of these things in order to be able to have Docker in production. So if you end up with Flocker and Weave competing over the user's keystrokes when they want to actually deploy their containers, which is the case today, then it means that we've failed on the promise of a portable developer experience, basically. So what we've been working on is some sort of plugin mechanism which can find a place for these networking and storage plugins, and other types of plugins as well in the future. We're starting with networking and storage. And the right place for that, we realized, was as a per-host plugin. So you can plug a networking plugin and a storage plugin into Docker at the same time. And I think there's three things that need to be achieved for this plugin effort to be successful. The plugins need to be late-bound, which means that you need to be able to load them out of process. For one thing, Docker doesn't have dynamic libraries, so it's not possible to load something into the Docker daemon sort of after the fact anyway. But it would be really nice if these plugins could also be distributed as containers, so that we can reuse all the infrastructure in the Docker hub and the image format. It's also imperative that these plugins are composable. So you really, like, the whole point is that you can load a networking plugin and a storage plugin. And the third part is that they need to be optional. So when Docker ship, for example, a networking plugin, it would be really nice if that plugin was removable so that you could plug in someone else's networking plugin, and so that the users still have choice. So all in all, I believe that if we can achieve those three things, which we seem to be on the way to achieving, then we can end up with a healthy ecosystem of plugin vendors and lots of innovation around extending Docker in interesting ways, but without ending up in a big mess where everyone's fighting over the user interface. So in an attempt to help accelerate progress on this effort, because it was clearly important for us as a business, we invented a tool called Powerstrip. And Powerstrip is a prototyping tool for Docker extensions. And you could also say that Powerstrip is itself a sort of prototype of a Docker extension system. If you get what I mean, they're slightly different things. They allow you to prototype extensions. It allows you to prototype extensions, but it's also a way of experimenting around whether this is a good extension mechanism. So I'll tell you how it works, and you can judge for yourself. So the way that Powerstrip works is it's really quite simple. It's actually just an HTTP proxy. And it's an HTTP proxy that sits in front of the Docker server and pretends to be Docker. So anything that speaks the Docker remote API can talk to Powerstrip, and its requests and responses will be handed straight through to Docker, and the response will be handed straight back to the client as if nothing happened. And it was kind of interesting implementing this because the Docker remote API isn't actually HTTP. It's a strange sort of mutant variant of HTTP, and so there were some edge cases that we had to handle, like half-closed TCP connections to indicate framing. But anyway, that was kind of fun. We ended up building this thing, though, and we got it working for all of the common Docker remote API endpoints. And the interesting thing is, I said that the requests get passed to and fro unmodified. Well, that's not actually true. They get passed to pre-hooks and post-hooks if those pre-hooks and post-hooks have been loaded. So when a request comes in from the client to the Docker daemon, Powerstrip allows these what we call adapters, which are these prototypical plugins, to have a go at the request and say, oh, I want to change this request, or I want to delay this request until I've done something on the system. So basically it gives Flocker and Weave a place to influence the state of the system as an orchestration tool, which could be the Docker, which is represented here by the client. So either the client itself, the Docker CLI, or an orchestration tool will be talking to Powerstrip, and it gives the pre- and post-hooks a chance to sort of have their way. And just in case anyone's interested, we just defined the simplest possible protocol we could imagine for these pre- and post-hooks, because we wanted to make it easy for people to experiment with this stuff. And so we were like, well, what's the simplest possible protocol? So we came up with just JSON over HTTP. And so the Powerstrip protocol allows you to do pre-hooks, and then it passes through the client request from Docker, and then the response from the hook. So by the way, to implement a Powerstrip adapter, you just have to implement an HTTP server. And that's pretty cool because it's really easy to implement HTTP servers in a wide variety of languages. And it means that people have been able to start extending Docker without necessarily having to use Go. So I think that's pretty cool. And anyway, so Powerstrip enables composition of these prototypical Docker extensions. And and that really helped sort of satisfy some demand amongst this community of people who are trying to extend Docker in interesting ways and add new functionality. So just quickly, I'll show you a demo of Powerstrip working. So I already talked a lot about Flocker. That's obviously the product from my company, Cluster HQ. It allows you to have portable volumes for Docker so that if you have a database, for example, you can move that database around, or if your orchestration framework reschedules the database, then it can be run somewhere else and not lose the data that it was holding on to. So it's useful for databases, basically. And Weave is a virtual overlay network so that containers can have IP addresses. And so the idea here is that Weave gives you portable IP addresses within a container network, and Flocker gives you portable volumes. So we've got networking and storage abstractions that can allow us to move containers around as a unit without losing their references to their networking and storage resources. And both of these tools wrap Docker, which sucks. But both tools can work together if they're Docker extensions. And so at the time I wrote these slides, I had a little asterisk that said, Docker extensions don't exist yet, so we'll use Powerstrip as a prototype. And that's changing, but it's still a work in progress. But anyway, so just using the Powerstrip stuff, Powerstrip Flocker observes create requests. It creates or moves volumes on demand. And those create requests are through the Docker Remote API. And Powerstrip Weave observes both create and start, and hijacks the entry point and does some fairly evil hacks in order to get it working, but it does work. And so just to give you an example, this is what a Powerstrip config looks like. It's just some simple YAML, and it says, oh, please intercept all requests to containers create, and pass those requests before they get to Docker as pre-hooks, first to the Flocker adapter and then to the Weave adapter. And the thing that's nice about that is that those Flocker and Weave adapters can then just be implemented as containers that are listening on HTTP on a socket, and they can do their stuff. So Flocker can move a volume in place, or Weave can set up an IP address on its internal network. And so just really quickly, I can give you a demo now of Powerstrip working. So what we've got here is 2 machines with 2 Docker daemons. And so what we're seeing is that we've got some containers. We've got a crate container which we're going to run. And notice that the crate container has a Flocker volume, which is just special syntax like /flocker/crate01. The crate01 piece there is pulled out and used as a global volume namespace. And there's also an environment variable that specifies the Weave IP address, which you might have seen just there. So we can see we've got the crate container running on the machine up there, and we can request some data from it, and we get some data back. We can now see that, indeed, that crate container is running on the top machine, just like in my previous demo. We can remove it from there, and we can start up technically it's a different container, but it's got the same IP address and the same volume and the same image. So it's effectively the same container on a different machine, and it will work. So that container came up, and the data that was in the first one showed up on the second machine. And notice that the interesting thing about this demo is that it demonstrated both Flocker and Weave without using the Flocker or Weave command line interface. It just used the Docker CLI. And that's powerful because it means that different extension authors or different plugin authors can develop different plugins, and that they'll work within. Basically, it gives operations people choice about which technologies they want to deploy on their cluster, but gives developers a portable developer experience using the Docker tools. So that's about all the time I've got. I just wanted to very quickly show you that we have, in the last few days, got a demo of moving a database with Docker Swarm also working. So the demo I showed you there was just using the Docker CLI on 2 different machines, but now we've got this working all underneath Docker Swarm. So that's a combination of Swarm, Flocker, Weave, and Docker, and Powerstrip. And just one other thing I wanted to make really clear about Powerstrip is that the Powerstrip project will be a success if in a few months we can throw it away, because Docker extensions have come out and allow us to implement the functionality that we need. And just very, very, very quickly, you can try out this demo yourself with the Swarm demo, that is, on our blog. There's a diagram of how Swarm is at the top, co-located on a master node with the Flocker control service, and that you've got two machines. And the scenario in the blog post is that node 1 has a spinning disk and node 2 has an SSD, and we want to move the database that's on node 1 onto node 2. And so this is sort of the before, and then this is the only transition I've used in this deck, I promise. And magically, the database appears on the right-hand side on the faster disk. So you can try that demo yourself on our site with a Vagrant demo that you can just spin up and play with. And yeah, that's about all I've got. So thank you very much.